Well, hello friends. Welcome back to the program. Today we are going to do something a little bit unusual. Linus has a virtual machine running Serenity on serenity.linus.dev, which anyone can control. And as you can see here, some hilarious person has logged in and deleted all the files. And as you can imagine, it breaks the machine until Linux fixes it. But yeah, so one thing that frequently comes up regarding this virtual machine is that it's hung in some state and Linux can't figure out what's going wrong, and there's no information on the debug console. So today I'm going to add a mechanism where you can press a key in Serenity, and if the kernel is able to detect the key press, then it will dump out some state. Basically, I'm thinking we'll just dump out the current thread table, like all the threads and what their states are. So you can at least get some idea of what might be running, what might be stuck. And the idea here is to help Linus debug whatever's going on the server. Of course, it's not going to help with this situation, but in this situation, it's fairly obvious what has gone wrong. Anyway, that's the background of what we're doing today. So I'm thinking that we will put something in the keyboard interrupt handler in the kernel. So essentially, let's see, where do we get IRQs? IRC. They're not here. Okay, I guess, do we get them from the 8042 controller? Keyboard device, yes. Okay, IRQ process input buffer. So the I-8042 stands for Intel 8042. That's the old style PS2 controller found in PC systems that controls both the mouse and the keyboard. So on PC systems, the mouse and the keyboard share I/O ports, which is a little bit irritating sometimes, but once you figure out how it works, it's not such a big deal. Anyway, we can see here that when we have data intended for the keyboard, then we end up calling PS2 keyboard device IRQ handled by red. So this is where we go. Okay. And then we interpret the key. So basically we're getting raw keystrokes coming in here as scan codes, and it's not, at this point we don't know anything about whatever language you might be using, which keyboard layout or anything like that. All we know is we get like a raw number that encodes the placement or the position of the key on the keyboard. But for many keys, that can usually be enough to figure out what it is. As you can see here, like Alt-GR, Alt, Control, Super, and Shift, they are hard-coded things. I guess this is left and right shift, which we both treat as just shift modifiers. Anyway, so I think here, if we just enable this debug statement always, we can actually, just by running the kernel and pressing some keys, we should be able to see some raw key codes. So this right here, I'm pressing F12, that's F11, which of course is the full screen key. But I'm thinking maybe F12 would be a good state dump key. I would use the sys request key, but my keyboard doesn't have that. So I don't know. I mean, I have, it's usually on the print screen key, and I have FN print screen, which gives me 5D. But for whatever reason, that brings up a context menu. So I'm guessing that this is the context menu key. Wow, I never knew that that was a context menu key. Oh, it works here too. Oh, that's so interesting. Well, I just learned that I have a context menu key on my keyboard. So then it's clearly not sysrequest. So let's just use F12. I think that'll be just fine. So that's hex 58. And then we don't need U anymore. So I guess we can just put that up here. So like if byte is hex 58, F12 pressed, dump some kernel state to the debug console. And you know, in the future, this should probably be like an opt-in thing. And in fact, we could make it a little more esoteric by requiring some modifiers. So we could say like modifiers equal to, I don't know, like mod alt, mod shift. So alt shift F12. Let's see how that feels. I mean, I didn't do anything in response to it. Do stuff. So F12, nothing, shift, alt shift. Yeah, there we go. Alt shift F12. That feels like you're not gonna press that by accident, right? So alt shift F12. But in the future, we should probably have a compiler flag that allows you to disable this completely. But I think for now, maybe we'll do something like scheduler dump scheduler state, let's say. And yeah. Okay. Right here in the, wait, scheduler is a class? Okay. I have not touched the scheduler in a long time. All right, so how does this thing work again? I guess this will be called with interrupts disabled, presumably. So do we have something like for each thread? How do we iterate the thread list? What do we have? Thread list, the thread ready queue. We have a bunch of ready queues. What if I just want like all threads? I feel like somewhere is a piece of code that just dumps all the threads. I just forget where that is. Or maybe that is... Maybe we've lost that code. No, this looks like what I'm looking for. Pick next. Scheduler thread list for processor. Yeah, this thing right here. So let's do something like this. Dump thread list. Oh, and it's just using thread for each. Okay, that's fine. So we'll put this in a helper. Dump thread list. Dump thread list, let's say. Okie dokes. And oh, my IDE is set up for 64-bit, but ignoring that. And actually, we don't need to rebuild the disk image. When you're only editing the kernel, that's like the one time that you can restart the system without building a new disk image. If you're touching user space, you have to install user space into the new disk image. But if you're developing Serenity and you're only editing the kernel, you can just do Ninja and then Ninja run. Fun fact. And of course, I didn't tell him what the return type was. So let's see what we get out of this. So of course, this will only be for that one CPU at the moment. And we would want to do this on every CPU, but I think right now, let's not worry about that right now, because we're only running on one CPU here anyway. So I'll shift F12 and look at that. The scheduler thread list for processor 0. Isn't that nice? So what do we see here? We see the state of the process, the priority of the process, or rather threads. And then there's a PID and a TID, and you can even see where, which segment and EIP, like address it's executing at the moment. So that's really awesome. I think this is probably already quite helpful, because then if the system hangs, you should be able to see here, for example, that like, well, what would you see? Like you would see that Windows Server is dead or something like that. That's why you don't have anything on screen. But certainly better than nothing. Maybe it would be cool to show like how many times each thing has been scheduled, like, which is basically how much CPU time a process has used, because then you could like keep hitting Alt-Shift F12 and you would see if somebody is burning CPU cycles because they keep getting scheduled. So let's add that. So we have the state string, and EIP, and then I guess we'll put the cycles before the, wait, what is this? This is the name. So let's widen that column a bit because it wasn't quite large enough. And let's also widen this thing so it's symmetrical. And then let's put times scheduled at the end, maybe. Something like that. Times scheduled. Yeah, and for like threads that are dying, if you have a thread that's dying, then it would be good to learn about that. So we'll print that as well. Okay, it's getting better. We need to, yeah, so you see what I mean here? Like if I just hold down Alt-Shift F12, you can see which things are advancing here. This means that this thread was scheduled, so it ran and did something. Like this terminal here is blinking, that's why it's getting scheduled. So we need these to be a bit wider. Let's say 30. I'm feeling like 30 is going to be just the right number. Here we go. That's pretty cool. This is extremely uninteresting because because all of them I guess this is just the context switch, the address of the context switch in the kernel. So wait, so how can we work out where they actually are? Register dump from stack, CS. EIP, we can maybe do this. Let's try it. Oh, that did not go well. Okay. So not everybody has a trap. Oh, shoot. Okay. Okay, wait, let's fix this up. So if, oh no, get CS for thread. Let's make some helpers. And then if there is no trap, then return CS from the thread state segment. Otherwise, get it from the register dump on the stack. I think this will work. It's a little bit hackish, but let's try it. Okay. Okay, that's really cool. So now you can see where it actually is running, not just showing the address of the context switch in the kernel. But in this case here, this is the one that was failing. Oh, because it's the network task, I guess. Yeah, it's the kernel task. Yeah, so you can see the address in user space if you want to look that up somehow. It's probably not going to be super useful because of ASLR and everything. Still, it's the start. And then we can always add more stuff. This is just the thing that came to my mind. But now at least we have a place, we have a mechanism for pressing something, Alt-Shift F12, and we can always improve on it later. So let's just commit this. Dump scheduler state. Add magic key combo Alt Shift F12 to dump scheduler state. This might be useful. Pressing this combo will dump all the threads, dump a list of all threads and their state to the debug console. This might be useful to figure out why why the system is not responding. The system is hung, let's say. Is not responding. Yeah, let's say. That's cool. So I think that's really all that I wanted to do here, and we have now done it. So I hope this will be useful to Linus and maybe to other people as well who just want to know what the system is doing at any given time. If you ever run into a hang, you can now also press this and include that in your bug report. Yeah, so very short video today, but I did what I set out to do, so I'm happy. Thank you very much for hanging out, and I hope that you saw something interesting here, and I will see you next time. Bye.